Let's go ahead and get started here. So thank you everybody for coming. It is my pleasure to introduce Jonathan Freund to anybody who hasn't met him before, or welcome him for all of you who know him. So he is the head of aerospace engineering at University of Illinois, Urbana-Champaign, also the Donald Bigger Willett Professor. He has many accolades to his name. I'm not going to read the whole list unless you want me to.
I would suggest none of it.
Okay, I mean, I could.
No.
Sorry, it's getting late in the year. So he does a lot of computational science around fluid mechanics, and in particular, hypersonics, which I believe is what you're going to talk about today, right?
It's one of the things.
Okay, one of the things, the computational work in fluids.
The simulation.
Okay, excellent. All right, so I think with that, I'll just turn it over to you and let you get started.
Thank you, Christy.
Yeah.
I love the informative introduction. I think that's right. Let me hide this again. Okay. Hopefully we're good. Okay, so this is kind of the outline rather than a title slide, actually. The talk actually has three parts that are interrelated, but it's not going to be tightly linked. First thing I'm going to talk about is the center I direct, and it's a large scale predictive science effort. It's got lots of pieces in it. And it's hard to go a whole talk like that because it's hard to get deep onto anything if you talk about that. So I want to tell you about it though, because I think it's really exciting. And then I'm going to tell two short stories, and they're kind of like projects that exist within this center and some bridged into the one before, because I wanted to have things that have results. And so these will come up as we go along. Let's start. So I want to define what PSAP is for you, because in order to understand this big project I'm going to tell you about, you need to know kind of where it comes from, because it's kind of unusual. It is a DOE, NNSA, ASC PSAP center. That's the Center for Exascale-Enabled Scramjet Design. NNSA is the National Nuclear Security Administration. So it's half of DOE. The other half is Office of Science. ASC is the Office of Advanced Simulation and Computing. And I just let them in. Maybe someone else should have vetted who that was.
It's okay, we followed the rules. There was a waiting room. So
okay, and this grew out of the Test Ban Treaty in the early 90s. And it was switching from test-based competence in the main application of the National Nuclear Security Administration towards simulation-based. And so it's motivated by that and doing simulations of the devices that the DOE works on. But they don't want us working on those devices. We don't want to work on those devices, but they want predictive science to be an academic discipline, and a vibrant academic discipline. And that's what this is about. And so it's using large computers and integrating multi-physics applications using advanced computational computer science tools to do true prediction. And they're large centers. This is a $20 million effort over 5 years. And there's a previous one at Illinois and a tangentially related topic that also existed over 5 years. We have to do these mandatory annual full system coupled physics predictions, and that's what links the whole center together. So I'm going to start off by giving you an overview of that. I'll talk a little bit about our predictive science topic, and understand within this, it's about workforce development. So training students that live in an ecosystem in grad school that exists in this larger way, and they can do their PhD dissertation. And so part 2 and part 3 are going to be basically 2 PhD type projects that lived within this center over time. And so we're talking about scramjets. And this is an aerospace department. Most of you know what a scramjet is, but it's a supersonic combustion ramjet. It is the technology for hypersonic propulsion in many ways. And so it has supersonic combustion, which avoids the deceleration compression losses in the engine of decelerating the flow from supersonic to subsonic. Going through the shocks causes excessive dissipation and makes it inefficient. And it's air breathing, which unlike a rocket avoids the weight of carrying your oxidizer. So that's very attractive. A significant fraction of the weight is saved. It's nominally simple. It's a duct with fire in it, but the extreme conditions make it very challenging. It enables access to space, global transport, next generation delivery systems there. And so we're not just doing scramjets. That would kind of be single physics as far as one of these centers is. We're also adding this to it. And we want to use advanced composites within scramjets. And so what you want to think about this is using the same sort of technologies that are used on heat shields on entry systems, but within the engine and for lighter weight. And then how do you do that is sort of what we're trying to answer. And there's a whole array in which you can take carbon-based fiber composites, all of them here, and use them. So some can be dense and strong and heat resistant, other are porous, more like what we've seen on, say, the Apollo re-entry missions. You can also make fabrics. Some of these look like fabrics, and you can actually make flexible composites here that are also high temperature. So we're exploring a lot of these, mostly this type in the combustor at this stage in the center. They all have common features, talking about carbon fibers and then something on top of them, a phenolic that will outgas, or ceramic, which would make it highly heat resistant and strong, and exploring this multi-parameter design space. And the whole reason to do this is to avoid flight tests. They're very expensive, and there are very few of them for scramjets. Here's a short list of ones over the last 20 years or so, and we'd like to impact the design cycle. So flight tests are incredibly expensive and inflexible. Ground tests are pretty hard too, if you want to talk about matching the actual evolution of a mission profile for a hypersonic flight vehicle. This is an example of that. This is the, I guess it's Tunnel 9, I think it is, at NASA Langley. It's a building size operation. It can do a limited range of Mach numbers. It also involves things like 70-foot diameter vacuum spheres. There you get a sense of its scale. And so underlying hypothesis of the work in the center and what makes us a predictive science center is that physics-based predictions will accelerate design innovation in this space if we can kind of bring them to the next level. And now we don't have a facility like that, but we have something that's close. And this is a much smaller scale experiment on the U of I campus. And this is an ArcJet combustion tunnel. That's what ECT stands for. It was an Air Force built project. It's led by Professor Chung-Hoon Lee, whose name used to be here. I don't know where it went. It's his facility on campus, and he's part of this center. Low cost, rapid turnaround testing. And this, I'm just going to show you a demonstration of this and give you a sense of the type of predictions we're trying to do with our codes, which is the most work at the center. But we're going to test our codes against this, basically validate our simulations and establish predictive confidence. The ArcJet is over here. That dumps in a lot of enthalpy into the flow. This is a direct connect setup with a test section here. And so you get Mach 2 or 3 coming through here, but at enthalpies of hypersonic flight at Mach 5 to 7. In this cavity flame holder, we've replaced part of the wall with a carbon fiber surrogate material. And this is the very beginnings of heading towards these composites. And so this is just naked carbon fibers. We haven't coated with anything, but we expect them to break down in the 1 second operation of this. There's a fuel port here that's going to eject ethylene into this, and it'll be lit by a spark plug. And this is the carbon felt. Think of like felt like the fabric type felt, but made out of stiff carbon fibers. That's what that black stuff is. Oh, that was impressive. That's awesome. Okay, I'm going to play that again in a moment. So if anyone needs to cover their ears, I'll do that. In fact, let me play it one more time and then step you through it to actually show you what happened with some still pictures. This is the spark plug. This piece of blackness here, it's actually flushed with the metal. That's the carbon felt. It just looks black because it's so absorbing of light. That little thing right there is the ethylene port. And I think I just said that was a spark plug that ignites it. So I'm gonna try to play this again. If it's too loud, cover your ears or something. Or maybe we won't play it. Here we go. There we go. That was the most impressive time. What do you see here? Time 0. The spark plug goes. You can see the felt a little more clearly here. There's our fuel port. It switched its orientation, flows from left to right, Mach 2 or 3 coming in here. That ignites the ethylene. And there's this point where you see a lot of flame. You see little bits of stuff coming off the carbon, some little ablation. At 1 second, everything shuts off. The flow shuts off, the fuel shuts off, and it's glowing. And it glows for a couple seconds, and that's it. And so if you zoom in on that sample, and I hope you can see this out there. I'm not sure. It's very hard for me to see it here, but there are a bunch of little chunks missing here. There's significant mass loss from this carbon here, where this one is completely flush. And you can see the color changed further because it exposed some naked fibers and it had oxidized them a little bit. Sorry if you can't see that very clearly. It looks great here, by the way. The people on Zoom have a better experience for at least this little part of the talk. Predicting how much is going to be lost in a particular case is a step towards being able to then do predictive design using this sort of thing. Now, that was 1 second, and that was because there were naked fibers. We saw things go away. This is that same material, but in this case, we gave it maybe the fibers are coated with a phenolic that then is oxidizing. And so this is the top of a flat flame burner. This is that material, and this is a real-time movie. You saw it going on like that. It'll stay like this for up to 15 minutes, and you'll see little bits come off, but it'll really slow down the oxidation of this. And it's because that phenolic boils off, and it's kind of cool. It keeps this cool layer on the surface and protects it. And then what happens when you then have combustion chemistry plus hypersonic flow or supersonic flow over it is that's where the center is heading. And I'm glad that one didn't have a soundtrack. If we can get to the next slide. Uh-oh. No. Okay, we are on the next slide. I'm gonna hide this again. And so the overall center is trying to simulate all of these components. So we want to go from something that you might say is relatively first principles, bring in other experimental data as needed, and model across scales to do predictions. And so it has a range of scales. We have the full turbulent flames that you saw in the model Scramjet. We have little bits of material being broken apart from the carbon fiber composite. It's made out of carbon fibers with some sort of coating on it. Those oxidize, they disappear and they become brittle because oxygen is eating them away at the temperatures they're at. And that happens with a complex process. And that's mediated by kinetics of the surface. And so it has surface chemistry. And there's kind of like a hierarchy of different models and physics we know are going to be important, potentially important. And this is how you fill up $20 million worth of efforts here in one sense. And it really is this complicated and interconnected. The simulation approach, I'll say a little bit about this, and then we'll go deep on a couple things here going into it. So we're developing a code, we're calling it MergeCom. So this stands for our computer science story I'll get to in a moment. Brings together combustion is what that. Discontinuous Galerkin based. So it's a finite element method that's reasonably well suited towards compressible flows. It's attractive to us for a couple things. It localizes computational intensity, meaning it does a lot of work, but it doesn't need as much communication as some other methods. And that's good if you want to run on massive computers. Each can do their own work and they don't need to talk to each other as much. It has some provable properties because it's got a weak form description with unified boundary condition formulation. Good for geometry, so unstructured meshes, we can change our geometry, come up with a new mesh, or if little bits are flying off, we could remesh that. It's an attractive thing. So we have some experience in this. It's currently feature complete, so we can do this sort of simulation, at least in beta. And it's something we've developed in the center within our merge framework. And the cool thing about it and why we do this, and part of our mission is to use massive scale computers to get predictive confidence by resolving space and time scales. All of the turbulent combustion constitutes a lot of space and time scales. The fibers constitute space scale. It runs on out of the box on GPUs and CPUs. And this is what it looks like schematically. So people like me who do simulations and are less concerned about computer science, except when they're directing a center like this, sit over here. And it basically gives the user operators in Python that describe things. And so differentiation, computer flux, boundary conditions, right-hand sides. This is the pieces that make up solving equations numerically. And humans can read this very easily. So if I showed you this code, you'd be like, oh, that's solving the mass equation, that's solving the momentum equation. It's very, very easy to read and move parts around. Those then launch kernels. And this is human readable and written code. It's not the kind of thing you'd like to look at. It's the IJK loops of programming languages. And so those are computational kernels. So the idea is that you write them once and test them, and then they do that thing. You don't really need to look at them very much more. And then computer science happens in a real way. And so like the codes I used to write, and I guess I still do sometimes, this is about where you go and you compile it. There's some annotations added to these that allow these to be taken apart and put back together as kernels. So they provides abstract representations of them. And there's a tool called Loopy that basically looks at it and comes up with a loop polyhedral representation of the algorithm. So a geometric representation of the algorithm, such that it can be taken apart and put back together by transform tools, and then creates a DAG, which is directed acyclic graph of macrokernels. So it's like, these are your kernels, pieces of your algorithm, and you want to run on GPUs? Okay, this thing's going to take that DAG in, it's going to generate code. We usually use OpenCL, though there are other options, and that's going to run on a GPU or CPU. CPUs run OpenCL, or you just compile it in C, and it runs on a CPU. And that's how we get platform portability. And this taking apart and putting the algorithm back together is the key to efficiency. You can stack it up in ways that it can efficiently use the available computer resources, whatever the hardware is. So this is a summary of that. We call it merge for math, intermediate representation, generation, code generation, and then execution. And that's where the merge part of the center comes from. And if you have questions about this, come up to me afterwards. I can talk a lot more about this, but it's a little bit beyond my expertise. I do fluid mechanics when I'm not posing as a center director. The centers are organized around these annual prediction goals. So it's supposed to tie everything together. And so we started off doing a prediction of someone's former thesis. And we did a prediction basically of that video you saw, getting a very crude. And you start with simple models. You make your prediction, you realize you missed it by this much, and you have reason to believe this physics is missing. You enhance them the next year, and you move the goalpost for your prediction challenge. And so we're making it harder and harder each year and trying to impact design with some confidence in year 4. And we bring in more physics every year. We do better uncertainty quantification. That brings in auxiliary experiments. We have a whole suite, like that burner I showed you with the phenolic. That was an experiment we're going to use and maybe calibrate some submodels that come into the overall prediction. And we use this to validate our uncertainty quantification on some of the subproblems. We continue to develop that code within that CS framework. There are multiple PhD theses in this box over here about how best to do this and work with the kernels of the computation. And we're very aware of not just the runtime of one of these simulations once we actually do them, but the entire conception. This is the simulation I'd like to do, generate the mesh, run the simulation, post-process. That's the real metric of things. We can be confident that computations are going to get faster still just because of hardware for many years to come, but human time is going to be more or less what we have. And so improving workflow is part of what we do. These are all the people involved, and this is how it all ties together. And I guess I could just stop here and go on. This is the level at which we try to link it up. These are those annual predictions. You have computer science projects, and a lot of these are students with their projects tying into things. You have some more physics modeling projects. You have some experiments projects. We have uncertainty quantification striping across the center. But this is one of my main things I do is help this all come together. Does anyone have any questions at that? And this is, I didn't want to just kind of keep that high level talk going all the time. This is going to be a very abrupt change. And so students, you're told not to do this in your talks. It's going to totally change. We're going to dive deep onto one project after this. And if you have any burning questions about the high level center, I'd be glad to do it. I'd also be glad to dive into this subgrid scale modeling. Go ahead.
So going back to that kind of ablative experiment that you had at the beginning, is like the main aspect of the computational side specifically to predict like things like ablatives?
Yeah.
Or is it like more broadly focused for the computation?
It is to produce general results based on a specific goal. And so we set as our goal very specifically, and our program managers hold us to this very rigorously, is what exactly you're going to predict. And it was going to be the temperature rise within that material. We have some thermocouples in it, and the mass loss of it. And we get some numbers out of the experiments on that, and then we do it in the simulations. We keep it blind until the simulations are done, and then we make that comparison. Now, depending on that, we've learned something, and we've learned, well, we did a really bad job at it, and we then go into the simulations, and this part seems off, like there's obviously missing physics here because of this observation of that. So we've learned those general things too. And our uncertainty quantification seemed to work in the simple case, but didn't work on the full thing because we missed by our error bars also. And so that's kind of the more general things we learned. And then you go back and you say, well, what do we do next? And you build on that.
Right, and because of the building block approach that you guys have, then if I'm understanding this right, your hope is to kind of retask it for future things.
Yeah, yeah. And so the ultimate thing is to have established predictive confidence in year 5 to the point where you could then have an impact on designing something down the road. And really being held to do those specific cases they know what they're doing when they're pushing us to do that, because it really focuses on actually doing something rather than just kind of thinking we're thinking about it. Any questions on that? Yeah.
So I have a question when you did on so I'm kind of curious, like how you make it to Mach 2, speed of Mach 2.
In the tunnel? So
Can you use a different propellants or like?
you get Mach 2 from high pressure, and then you get high enthalpy by an arc jet that dumps kilowatts of energy into the flow upstream. And between those, that's how you get that tunnel from Mach 2. Does that answer your question?
So you're now using like specifically like temporal equations.
We, in this center, we have not modeled that arc process, but we take it as inflow boundary conditions. In the previous center, which was called the Center for Exascale-Enabled, no, that was plasma coupled combustion. We actually did model what goes on in that arc jet driver and went from chemical kinetics equations and voltage across the electrodes to predict the flow as part of that center. And that came along. It never got to the point where actually there was a paper, which is one of the risks in tying things together. That's why I've kind of emphasized that the PhD projects are nice, well-contained things within this that lead to dissertations. And that's really important for what we're doing. And some other things the center staff works on, and paper or not, is less important for them. I'm going to jump into this now, but I'm glad to talk about this. It's one of my favorite things I do is tie everything together there. One of the other favorite things I do is a couple of these projects, and this is a machine learning with subgrid scale modeling. And so I was with a couple of collaborators. John was with me. They were both at Illinois when this started. John was working with me in the very beginnings of this center and at the previous center we were at. He's now a professor at Notre Dame. Justin was a colleague over in engineering there. He left Illinois to math at Oxford, and I'm here. And this is what we want to simulate. This is flow turbulence. This is just a shear layer here. But you can get a lot of important stuff out of a simulation like this without representing, like, this eddy doesn't matter for the time average in its detail. And so you would like to use a nice coarse mesh to simulate something like this rather than resolving all of these length and time scales. You know, if you can resolve all the length and time scales, you're going to get the physics right in this case. You would like to do it a lot less costly than that. And so that's what this is about, a machine learning way to try to do an LES, a large eddy simulation of this. And we developed an approach for this, and Justin developed this name, Deep PDE method. That's what DPM stands for, and it's a closure approach. And so let me just give you a schematic of first a prediction, and then tell you our way of bringing machine learning into it. And so that's kind of the most direct way to do this. So let's say you wanted to set up a machine learning model for that subgrid scale closure. Well, you have some known physics plus something that you're not representing, and it'd be our small scales here. I'm much more interested actually in, like, if it's flames or some other processes, but this is just missing scales at this point. You got your partial differential equation plus some terms in it that are closures. So if you filter the Navier-Stokes equations, you end up with unclosed terms. That's what this is, and you can make your prediction. Okay, now you want to use a neural network to represent this closure. So what you can do is try to optimize it. So you have the neural network predict the closure, you compare it with trusted data, you update the weights in the neural network, you keep doing that in a cycle and optimize it, and then you go ahead and make your prediction. And so what does that look like? Well, you've got your filtered Navier-Stokes equations, you've got this closure term, you've got your divergence of velocity equal to 0. You define some distance between the closure and your term, just the D operator. And then you have a gradient optimization. It's dependent of the loss function, which is that mismatch, on the weights of your neural network. So it's just a gradient. And if you have a gradient, you can improve things. That's all that does. It's just optimizing the weights of the neural network. And you break that into two parts. Depends on how the loss depends on this. Well, that's analytic formula. And then how this depends on the weights. That's the back propagation algorithm of a neural network. That's how neural networks are optimized. You get a gradient. That's how does the output depend on the weights, and you improve them. If you think about this, there are two real serious problems for doing this. Somehow you need a trusted model for the closure data. And so I can get this from a detailed simulation, like that picture I showed you. That's a direct numerical simulation. It's trusted, it's right. If you don't know the subgrid scale physics, you don't have that capability. And experimental diagnostics for things that are small scales, of very high frequency, very small scale, hard to get. And so you need that. So how to obtain that in general is hard. And it needs to be the same as the closure. So that's the problem. And then there's the bigger problem. Notice that this optimization loop never touches the PDE, which has the known physics in it. I mean, what could go wrong if you're leaving out the physics? Well, you don't necessarily obey the physics, and that's no small problem. And so this is what we did, and it looks very similar, except there's this distance. So we actually go back into the combined system now. We got our neural network, we got a closure guess. We actually solve the system coupled with the PDE, make a training prediction, compare it with trusted data, and then you have this other challenge of how to optimize this, because you have the adjoint PDE as part of this. And so what I mean there is that how does the loss function depend on the weights in the neural network? That's what this gradient means. Well, now it's got three parts. It depends on how the loss function depends on the solution. So think of that as a velocity field, for example. Then how that solution depends on the source term in the governing equation. That's this one. And then exactly what we had in the direct approach. How does that closure depend on the weights? That's your neural network sensitivity. So this middle term means that you have to come up here, figure out the gradient of this PDE, meaning how does its output depend on what it has coming in. And so you have to solve the adjoint, and that's makes this optimization a lot harder, but it's not impossible. It allows you two things. One, it's now touching the physics in the optimization. The PDE that represents the physics is in the optimization loop, and so that's good, we think. The other thing it allows you to do is this no longer needs to be exactly the closure. This could be whatever comes out of the governing equation. So if you solve the governing equations and average them in time and compute a mean flow, you can use that. And that's something you can do in an experiment. And that mean flow may depend on the subgrid scale closures. In fact, it will in general. And it's a way to use experimental data for this. And that can be different than what the closure is. So that's the setup.
Hey, Jonathan, question.
Yes.
So there's a lot going on these days in machine learning around discriminative versus generative models. I mean, this is a neural network, not specifically
Yeah.
a Bayesian kind of structure,
Yeah.
but is there any similarity there or connection?
Yeah. So
Because I mean, there's a similar flavor to like what's going on in discriminative systems if
Yeah.
you don't have that connection back to like the physics or the.
yeah. So I'm not an expert. I'm not a very broad expert in machine learning. So I'm not sure I know the answer to that. The physics here is not changing. So it doesn't need to track changing physics or anything like that. It is one reason it's maybe that's not the best way to parallel this. The way I think about this, maybe just say what I know. We just got a nonlinear fitting function in this, and I'm just figuring out a good way to bring that into the governing equation such that it can be maximally constrained by the physics. And maybe I'd need to understand your question better and give a better answer. But no, I'm not thinking of anything beyond in that direction. And so for my demonstrations here, it's going to be turbulence, large eddy simulation with a subgrid scale stress closure. I've already let you know that. This is the subgrid scale stress closure. It depends on the weights here. I'm just going to predict velocity fields. That's the outcome of the PDE solution in this case. Incompressible average dose, neural network subgrid scale motor. We trained for 5 time steps of the large eddy simulation, which is 50 DNS of the 50 time steps of the trusted data we have for this demonstration. Our input to the neural network is just local flow velocities. So it's what you have available nearby. And we use a discrete exact adjoint average solution of the average dose. And it's easy to say these things, to actually solve them repeatedly and do all the data management. There's a lot in doing this, and that makes this very hard. Even though hopefully I've shown you a simple thing. It's just a standard neural network. Justin made this up. It seemed to work, and we haven't really changed much except trying out the number of hidden layers and so on. Nothing's very sensitive to that. And like I said, I only just wanted to fit something. I didn't really want to try to optimize the network here. And just show you the results for this isotropic turbulence. So this is turbulence in a box. And so there's your turbulent field. This is the spectrum, and it's a very symmetric spectrum the way we have it. Here are your large scales. You're going to represent these well. You can discretize accurately on these scales. These you don't represent well. They have only a few points across them. And then we'll filter it down to these pretty aggressive large eddy simulation grids where you're going to throw out all the physics of all the higher scales than that and try to represent them with a neural network. This is a 1024 cube simulation. That's a lot of points. I think here's some details on the numerical methods if anyone's particularly interested in those.
What's the Reynolds number there?
I don't know. This actually gives you the Reynolds number for turbulence in an isotropic box is related to the range of scales, and you can see that here. I think it's RA lambda like 120, something like that. So respectable. 1024 is pretty good, but of course it's not experimentally high by some measures. I'd have to check that. I'm sure it's in the paper. It just wasn't. The spectrum was more foremost in my mind when I was thinking about this. And so this is a result. This is the energy in different scales in the large eddy simulation. The symbols are the DNS, the black circles. So that's considered trusted. These are just scaled. We've cut the filter off here. This is a 1/16th size of the mesh, so that's a lot fewer. So it's 16 huge smaller mesh size. And the new model are these red and blue curves, and they're pretty much over the data. Using established models, so these Smagorinsky models, a couple different flavors are here. So they work great, except they can't handle this aggressive of a filtering, and leaving out any model, you get this blue one here. And so you go from pretty off to pretty much on the data here with this approach. And it's qualitatively better than that direct approach. So if you take the first approach where you only train on the mismatch with the subgrid scale model and you put it in, so you take the same neural network, and rather than training on a prediction from the PDE, you just train on the source term. It's a heck of a lot easier because you don't have to solve the joint of the governing equations to do that. You get this red curve here. This is the energy in the turbulence versus time. And symbols are the trusted data. Our new model tracks that pretty well. It's pretty faithful to it. Just training in that a priori way where we don't solve it. It's even unstable. It starts to qualitatively incorrect, even with the same neural network. So this including the PDE and the optimization has a fundamental improvement to the model, to the results. So isotropic turbulence is great. Here's another one that I actually have a Reynolds number for, 6,000. It's a planar temporal jet. So it's got a velocity profile like this. It goes to infinity, up and down. It's periodic into the page and periodic in the streamwise direction. So it's growing in time as the turbulence is doing its thing. And if you just filter the trusted solution, you get a blobby version of that visualization of dynamics, Smagorinsky LES model. And here's our new one. So just to give you a sense of how much coarser it is, we're modeling all of these little missing bits between here and here. Quantitatively, it again does very well. The DNS trusted here, our joint machine learning model, nails that. The a priori model, where we don't include the adjoint, qualitatively off. And it's qualitatively off even though it reproduces visually well the subgrid scale stresses here. And so this is the match of the stresses when you did the a priori training. And it looks pretty good. It's reproducing it, but neural networks fit well. The extra constraint is what keeps it sort of stable on the tracking the solution. Out of sample, we trained it on this jet going one way. Now we're applying it to like jets going opposite in the same domain with this sort of velocity profile. Again, it works pretty well. It's close to the data and it outperforms an established model rather than dynamic Smaggering speed is out of sample. And then this is, I think, maybe the most exciting result. Rather than training on the instantaneous velocity fields, just try to train on the evolving mean flow. And so just this shape, basically, getting the evolution of this shape right in time is what this is. And so the training and the trusted things are statistics on the velocity, and the closure is the same, so it's stress closure. And it's less accurate, but it captures the shape of this well in a well-formed way. And the a priori one has no chance on this one also. So ending this short story, neural network training using the adjoint PDE is part of the training. Good predictions, it outperforms established models. Even if you take into the computational cost of the evaluation, neural networks can be very fast on GPUs. And so it actually is fast, it's better overall. The simple model is wrong. It's not constrained to having the closure data available. We can train it on things like the mean field. Those for the people who actually think about LES, large eddy simulation is always linked to numerical discretization errors, and we're also likely correcting those. That's for the people who think about simulating turbulence. We've extrapolated. We haven't shown this, but we also get good predictions of scalar advection, mixing of a scalar field with the model, and then far outpaces the established models. My real goal in this, I was to demonstrate this just on Navier-Stokes, but I want more physics in the subgrid scales, and so things like flames is on my mind there. And the current center is trying to develop this for subgrid scale modeling of flames, because then you have a lot of physics packed into subgrid scales, and it's really expensive to simulate that. Papers, if you're interested, a couple on the method, an opinion piece about machine learning and fluid mechanics from a few years ago there. And anyone have any questions on that story? This is another one of those discontinuities in this talk, one of these things students are told not to.
In scramjets, one of the big issues, as you know, is mixing of the reactants. Did you notice in your overall strategy, if you were going to include that in the analysis, and in particular, if you were going to compare your results with some experiments?
So yes, I mean, so in the scramjet simulations, we're transporting our starter model, kinetics model, has 7 species, and so we have all of those advecting around and mixing in those simulations. And there's no way we're going to get the flame in the right place unless we do that well enough. Well enough is going to be hard to determine for things like temperature into the material, but that's critical.
It may be hard comparing the DNS with, let's say, high Reynolds number.
Yeah.
DNS with chemistry gets to be problematic.
Oh, it's very hard. Yeah. And so, but with this approach for doing the neural network modeling, we can compare on mean flame location rather than on that. And we can do that from an experiment. And that's I think one of the most exciting things about that approach. People are ready for one more short story. Okay, completely abrupt change. Okay, we are talking about laser-induced breakdown and ignition, and this was a student of mine, Jonathan Wong, who was just a pleasure to work with for several years. Oh, this is a movie actually, but it's showing you something. And now this is the optical breakdown of a laser, and then the movie is actually going to play in just a moment. You're going to see what happens next. It lights a flame, and so you have an unsteady premixture of premixture of I think this is methane and air. There's a little jet of methane here. It's just kind of like letting some out, and then that laser goes, and you see that go on. This is an exciting way to ignite flames. And because you could like across the room, if you focus a laser, you could get something to start burning over there. And that's just, I mean, that's just awesome. And if you want to light something in the middle of a scramjet or something, someplace where it's really hard to start a flame, it's an interesting technology. It's also got fantastic physics in it. One of the reasons I'm excited about it. So that movie, I think we'll play again on the next slide. So let me just let that go. I think this is actually going to play, so you can watch it one more time. And so you see some variations indexed in the Schlieren, and that's just the mixing. And then there's the laser pulse. You get a blast wave, and then it obviously ignites. So what happens there? There's a lot of physics that's not going to be part of this, but just to head off questions. First thing happens is if you have two photons happen to hit or interact with a gas molecule at the same time, you can knock an electron off. And so that happens statistically, but pretty slowly actually. You get a couple free electrons, they respond really strongly to the electric field associated with that focused laser. And it rapidly becomes opaque because one electron makes more electrons. So that happens over a picosecond. And then on a nanosecond scale, you go from, well, you double the number of electrons really rapidly. It basically becomes opaque. And if it's opaque, the laser doesn't go through. It's all the laser energy suddenly deposited there. And 50 millijoules isn't a lot of energy. But if it's in a really tiny spot, it's really high temperature. And a plasma forms. And then a lot of things happen. A blast wave, a shock gets sent out. You can hear these across the room, and like a snap. There's all kind of plasma reaction, and if there's a premixture, like in this case of fuel and oxidizer, it starts to burn. And that's on a kind of microsecond time scale. And so I had a movie. Now, this is some of the really interesting phenomenology about this. And so I'm going to kind of ask a couple of questions, and then we'll dig into the piece of it. And so you can't see it here in the Schlieren, but there's a hydrogen fuel jet, low Reynolds number, just kind of going up here, surrounded by air. And laser focus from this way, nominally on that point, 10 millimeters here. And you see it ejects fluid to the left here. And when that fluid encounters this, it ignites. You suddenly see it blow up. And then look, it just, this kind of flame ball forms, which is pretty cool. It's only 30 millijoules of laser energy. And this jet, yeah, if you can see the times, not a lot of time between these. This thing's going 30 meters per second. And that kind of strain rates can also extinguish a flame because it's a high strain. So there's this weird balance going on. And so seeing things like this, why does fluid eject? Why did it go this way are the types of questions. And so how did it happen? So those are the types of questions we're going into here. I think there's more questions here. And so here's another thing. And so these are visualizations at very short time. So this is at 10 nanoseconds of different plasma kernels in different cases. So this is argon. You switch to air at the same pressure. It's got this weird shape. Lower pressure got a different shape. Lower pressure still, it's got a different shape still. So it's changing. Now, the weird thing is that ejection, like it was really pronounced in those last pictures, and definitely went that way. Well, that's what happens here. This isn't as great as Schlieren, but it definitely ejected to the left. This one didn't eject. This one ejected the other way. And the only thing that changed is you kind of like have the pressure and the density so on. It's all room temperature here. Okay, so why did it change direction? And then it probably has something to do with the changes of this luminous region here. So those are the questions I'm going to go after. We're not going to talk about the detailed physics. We actually did a lot of work on this too. We put together a 3-temperature non-equilibrium model for the plasma. We included multi-photon ionization in that model. Really, really small time steps when you're simulating sub-nanosecond phenomena. And we actually predicted experiments. The experiment is measurements of laser energy absorbed. In a couple of cases. We did a pretty good job with that. Very few empirical parameters. And that was one of the predictive science gems of the previous center, actually. And we predicted, these on the left are simulations predicting the glowy regions of the corresponding experiments. And they're not going to be point to point, but they definitely line up. And so it's good. So we're not going to talk about the physics that lead into that. We're not going to talk about plasma kinetics because this took some serious plasma kinetics in those models too. So here we were transporting lots of species taking really small time steps. What we're going to talk about is that ejection and what causes it and like those weird things like why did it change direction? And so we built a really reduced model for it. We asked the question this way, how the shape of the thermal deposition. And this is the thermal deposition of energy. We're just going to assume it's absorbed into the shape. And we know this is sensitive to the laser and the ambient conditions. My previous slide showed you that. And it leads to this weird ejection of hot gas, and it's a reversal, or sometimes it doesn't eject. And so we came up with a two-parameter model. It's compressible fluid, axisymmetric, constant viscosity, Navier-Stokes equation. So we took out all of the plasma chemistry and everything. It's just, here's energy is deposited in this shape with two parameters, aspect ratio and asymmetry. And you can see how that'll come about. And it's based loosely on the changes in shape we see in this shape here. And so we've idealized this problem. And it reproduced some of the phenomenology. And so this is PIV of some laser-induced breakdowns measuring the vorticity. This is our simulation at similar conditions. And it's not going to be point to point, but it definitely creates similar features, top and bottom here, that type of ejection, similar amplitudes too. You get similar numbers. It's not going to be the same. We've really simplified the model. This is a measurement of temperature fields. And this is phase averaged over lots of cases. This is an instantaneous case of our axisymmetric model. And same thing, certainly qualitatively the same. We have much more resolution, really, really well resolved simulations. They have the benefit of having all the real physics in it. And I really like this one. This is a premixture of hydrogen and oxygen, just the lasers pushed into it. This is our simulation with a kind of a false shadow graph here. It's just the able transform gradient of density. And the bottom's the experiment. And then this is a Schlieren of the colors, I guess, reversed from how you usually see it. You get these kind of weird lobes, and yeah, sure enough, they get those in the corresponding experiments. We're capturing some key things from this process. Is the bottom line there. Easily, the green check means easily enough to go on and study this. And so Jonathan did a big study of different cases. And so this is the radius ratio. So the size of the two ends. And if you change that from a small number to a big number, obviously it has to reverse because it's exactly the same thing going the other way. So that's left to right, totally expected. You change the length of it. So make long as high aspect ratio, kind of squat. That's the other way. It also changes the ejection direction. It goes from a strong ejection to the left down here to a weak ejection to the right, but it actually changes directions. And you can see the visualization of these things. Okay, why? Why does it eject to start with, and then why does it change directions? Well, they look like vortex rings. They look just like if you were to blow a smoke ring with a pipe, for example. It looks like vortex. Okay, so where does the vorticity come from? And then how does it interact? So we've boiled the main question into these two sub-questions. Writing down the governing equations, there's only one place the vorticity can come from, and that's baroclinic torque. So the vortex transport equation, axisymmetric. This is the only spontaneous source term. And it's the misalignment of pressure gradients with density gradients. And so this is my cartoon. And if you know about baroclinic torque, you know this, but I love talking about it, so bear with me. So if this is high density at the bottom, that's why it's dark gray. It's meant to convey high density. And this is lighter gray up here, and that's meant to be low density. So it's heavier at the bottom. And then if you have a pressure gradient, high pressure gradient is orange, and that's high pressure is pushing on this. It's easier to push the light stuff than the hard stuff, and it starts to rotate. That's all that cross term means. That's baroclinic torque. Okay, so it has to come from this, but where? Is it the shock? The shock has a huge pressure and density gradient. And in fact, curved shocks are known to generate vorticity, and we certainly have a curved shock coming off this oblong shape. It's not just the shock. Behind the shock, the pressure's got to come back to atmospheric pressure eventually. So there's a post-shock rarefaction, lots of density and pressure gradients in that. And then it actually kind of like, there's kind of like an expansion and then a collapse. Anything like create a low pressure region, then it has to collapse again. And so there's also pressure gradients in that. And so we stumbled around for a long time, and I could give a whole talk about the stumbling around. It would be pretty exciting because there are lots of parts to it, but it's also completely dull because it doesn't end well. It's the post-shock refraction. I'm just going to tell you the answer. It's in the region of non-constant curvature. So this is what happens if you put so this is a radius from where some energy was deposited. This is pressure. And this is the blue is for a spherical case. So that's maybe the easiest to picture. It creates a blast wave. Pressure suddenly goes up. That's the pop you hear if you do one of these. And then behind that, there's a post-shock refraction. It goes back down and it kind of bounces around a bit. If you do it for cylindrical ones, so this is the 2D version of it, this is what you get for the same initial pressure, same initial energy deposition. And so we started thinking about these elongated regions where the energy is deposited as having a spherical part over on the end and a cylindrical part in the middle of it. And in those cases, the pressure and density,
I got it.
okay, good. I'm gonna hide, I think I need to hide this still because it will distract me. Thank you. And there's in these regions where it's exactly a 1D problem, there's no possibility for density and pressure gradients to get misaligned. And so there's not going to be any generation of dirt in the short in there. In between, they get misaligned. And this looks like a cartoon, but this is actually data from a simulation. So here you can actually see them aligned here, misaligned here. And it's that misalignment you get across it's there, and that creates vorticity. Okay, that's where the vorticity comes from. And vorticity generally organizes into a vortex ring. And so it's enough to generate a ring. Then what happens? 4 things can happen, we observed, and you can think about the stumbling around that led to this story. Sometimes, and it all depends on the geometry of this, which one of these happens. Sometimes one pair of vortex rings just ends up being a lot stronger than the other, and it plows through the weaker ones and pushes them out, and that's an ejection to the left. Sometimes it's just geometric difference. So if you measure the rotation in this vortex ring and this one, it's just further out. And the closer one towards the center can scoot through the outer one. It pushes it out. And if you get closer to the center, you go faster. That's how vortex rings work. The self-induction gets a lot faster. It ejects to the left. Sometimes they interact before the second vortex ring forms. And so that's what this cloud means. It's like, I got a bunch of vorticity here. I haven't quite rolled up into a ring. Bam, blue vortex comes through, and it's correlated and it disrupts the other one. And then sometimes they're basically the same and basically the same geometry, and you don't get any ejection. In fact, they kind of splat out to the side. Those are the things that happen. And so I'm only going to show you 2 of those in some detail. I really only have like 2 slides left, so bear with me on that. And so this is the same aspect ratio, different radius ratios. And so this is the initial shape of the object. And see, so this end's a little pointier than this one down here. That's the difference here. And in this case, well, this is the plot of the vorticity, and the bottom line is that a vortex ring rolls up and ejects to the left, carrying some hot fluid in this case. In this case, you change it a little bit, it creates vortices that are sufficiently close in strength enough that they come together and do that splat one. So it's doing this in this case. And you end up them going out to the side, and it never carries the vorticity very far. This one's going 30 meters per second and will go that long way, like in the experiment I showed you. These don't make it very far. They get unstable in 3D, and so they wouldn't move. Okay. So that's kind of how they eject in cases. Now, this changing direction, that comes from this case here, is really what underlies that. And so these have the same pointiness on both ends, but this one's obviously a lot longer. And in this case, the vortex from the smaller end rolls up faster. It's more compact, less needs to happen in some sense before it rolls up. It punches through the other one, and it just kind of hangs around. In this case, they can both form. They're so far apart that there's time before they interact, they both form up. And the one from the left side gets to be a lot stronger. It just blows away the one on the right, with ejection going the other way. So it's something like that we think that underlies the changing of direction. If you go back and look at the glowy regions from those experiments, the change in direction seems to associate with more glowiness on the right than on the left, which is a thermal emission from the plasma. I don't like the word glowy. So to summarize this, I developed this very simple simulation model for laser-induced breakdown and induced hydrodynamics. The green checks, it seems to reproduce the key features of the experiments we were going after. We identified this vorticity production and evolution mechanism and leading to those observations. I'm not going to repeat what I said there. We've done a lot more with this. This is the edge of a fuel oxidizer boundary. And so this is the one that will then couple strain, which would help mix, but also if you strain something, it can put out a flame. It brings in too much fresh fluid and the flame goes out. And so we have a whole paper on this. I'm really interested in this as an addition source and a couple other things. Some papers on this. Jonathan was very productive in his times with me. And worked with lots of co-authors also in the middle. He's a great guy. Any questions about that or anything? Wow.
It seems to me that at least one of those transitions could be attributed to the Moore-Safman threshold for ripping apart a vortex, where the ratio of the strain rate to the vorticity is at a critical value. I think it's 0.15. So it may be, if you haven't already done it, that you can identify at least one of those transitions with the Moore-Safman result.
That would be really interesting. That's a great suggestion. I'm not familiar with that. I mean, I've kind of read a lot of Safman's book on vortex dynamics. I assume that would be a place to look. I'd love to write another paper with Jonathan. He was just a pleasure to work with. Thank you. We did not consider looking at that. Any other questions? Yeah, go ahead.
Going back to your experiment on carbon materials, Scramjet versus flame.
Yeah.
It seems to me that the two configurations are really different. And can you talk about what are the temperatures, what's the difference in temperatures and heat transfer?
So the two configurations, so I showed you like.
Sonic flow has a much higher stagnation temperature.
Yeah,
So
yeah.
compare the two thermally.
So. Yeah, so that stand burner is meant to be something that brings some physics to get and gives us a validation case with an axisymmetric geometry, so we can really analyze lots of parameters and calibrate our EQ. The flame temperatures there will get around, I don't know, or let's just say over 2000 Kelvin. The stagnation temperatures in the actual application are such that carbon starts to glow if you just run the thing, even if you don't have a flame. And so I don't know what temperature that would be, but we think that it's more like 3000, the surface temperatures. And, or actually the gas temperatures above the surface. We don't actually come to thermal equilibrium. So they're in different conditions, and that's part of our challenge. We could, I suppose, put I don't know, somehow get a hotter flame, maybe use acetylene, but we'd rather use the same fuel to get the same chemistry we'd expect, but even that. So your question cuts to the heart of some of the predictive science we're doing, and that they want to see us struggle with as part of these efforts. And so I don't know if I answered your question. Definitely, they're not in the same conditions. And I'm actually more concerned about the missing shear stress and pulling little bits off, because that'll expose fresh material in the Scramjet configuration. Go ahead, follow up.
Well, I'm also curious about the heat transfer configurations. Much higher than the sonic flow application.
Yeah, so you almost certainly get a thin boundary layer there, but you have almost a stagnant boundary layer above of the other case, and the other one comes to thermal equilibrium. So yeah, so yes, it could definitely heat up faster in the supersonic flow also. And so yeah, but again, it's one of the considerations. But for a lot of those things, we're pretty confident about the Navier-Stokes equations. And then if it's just resolving scales of those, we know how to do that. We just do a bigger simulation. We've got all these CS tools. We can run massive scale simulations. Running larger scales will never bring in an additional kinetic mechanism that becomes important for creating atomic oxygen, which will oxidize the fibers much faster than diatomic oxygen. And so we also have to ask questions like that, but between those and make sure that you have the species that'll react with the surfaces in the models if you need them. So your question is, it's an example of some of the many issues we wrestle with in applying this case to this case. And extrapolation is what we're trying to establish. And so the more models we bring in, we have an atomic energy cell, atomic oxygen cell, where we just simply heat carbon and put different environments on it and watch it oxidize and close some calibrate some surface kinetics models for that. This is another example of bringing in more physics. You had a question? Yeah.
Yeah, this one's also going back to some of the composites covered.
Sure.
You mentioned a few different insulation strategies. You meant like the coating, like phenolic coating.
Yeah.
Carbon, and a few others. Where did you kind of come up with all those different coatings or like
Yeah.
protection?
So they're kind of two, yeah, so the main one, our workhorse one right now is a material we're calling Harlem, or is called Harlem. And this is a open source version of what's thought to be Pika, which is a export controlled entry system, something or other, thermal protective system. And so we're basing it on something like that. And that's in the open literature, but we decided not to work on that by name anymore. We found a formula out there we like, and it's pretty much open literature. So it came from a known model that's used in the entry studies. And why did we start there? Well, because there's some data on it and we had some around. One of the questions I'd like to address, what would you like it to be? Because Scramjet's really different than a re-entry problem. And so one of those students on that massive chart with all the arrows and so on is looking at, let's just do a timescale level analysis of this system to try to figure out what properties we would like to have. And then the idea would be to say, well, obviously we need a lot more phenolic imbued, and we'd like to have a microstructure that looks more like this, a lot more carbon fibers or a lot less carbon fibers, and trying to figure out how to go that way in the future. We had originally started thinking we were going to use some ceramic matrix composites, which have actually been tested in Scramjets at that NASA Langley facility. A guy named, I think it's not Michael Glass. Anyway, forgot his name. There's a paper in AIAA conference where they replaced the walls of a Scramjet model with ceramic matrix composites and fired it, and they melted the steel behind the composites. It was really impressive what they did. They didn't mean to melt it. It was just the outcome. And there's just a glaze, a silica glaze that formed on the surface of the composites. We've shied away from those also because those are becoming, not too many people want to talk about what their ceramic matrix composites are these days. And so we wanted to keep this more academic. And over the past 5 years, the hypersonics materials research has just become a little bit more restricted. And so we're moving more towards things that will illuminate our predictive science goals without being directly linked with actual applications.
As a quick follow-up, is there any textbook resources you would recommend for, I'm very interested in composites, and if there's any kind of thermal protection stuff, is there any resources you recommend for that?
Ooh. So
I know it's kind of a niche.
yeah, so there's a ablation workshop that was held about in the last couple of years, and they'll talk a lot about those materials and a lot about the modeling for them, which is tantamount to saying how do they respond to these high enthalpy flows. So search ablation workshop results, and I think you'll find a stack of papers there. I don't know of a textbook on them. I think you'll find some stuff.